Welcome to the another class of design of RCC structure. In this class, I am going to design a rectangular RCC footing with the given data. So let's check out the problem. First, as I tell you every time, read out the problem very carefully. Design a rectangular footing of uniform thickness for an axially loaded column of size 300 mm by 600 mm. Load on column is 1150 kilonewton. Safe bearing capacity of soil is 200 kilonewton per meter square. Use M20 concrete and Fe415 steel. So let's start the solution. WC, the column load, is given, that is 1150 kilonewton. So WF, the silhouette of footing, is equals to 10% of WC, as we know, that is equals to 115 kilonewton. So WC plus WF is equals to 1265 kilonewton, and the safe bearing capacity QU is equals to 200 kilonewton per meter square. For M20 concrete and Fe415 steel, XU max by D is equals to 0.48 as per IS 456 2000, and RU is equals to 2.76. So in last video I have shown you what is RU, how we can calculate RU, and a table which I prepared for different grade of steel and grade of concrete, the values of RU or K. So let's check again the table. So this is the table for M20 grade of concrete and Fe415 steel. The value of RU or K is 2.76, where RU is equals to 0.36 XU max by D within bracket 1 minus 0.42 XU max by D bracket closed FCK. Okay. So RU is 2.76 for M20 grade of concrete and Fe415 steel. Now the area of footing capital A is WC by WF by QU, that is equals to 1265 by 200, that is equals to 6.325 meter square. Now considering length to width ratio of footing same as that of column, that is 2. So y is equals to 2x. So area of footing is equals to x into y is equals to x into 2x, that is equals to 2x square, that is equals to 6.325. So x is equals to root over 6.325 by 2, that is equals to 1.78 meter, say 1.80 meter. So 2y is equals to 2x, that is equals to 3.6 meter. That means shorter length of footing is 1.8 meter and longer side of footing is 3.60 meter. Now the soil pressure due to column load is 1150 by 3.6 into 1.80, that is equals to 177.47 kilonewton per meter square, and to make it factor just multiply the factor 1.5. So that is equals to 266.21 kilonewton per meter square. Okay. So this is the soil pressure. Now calculation of depth of footing. So, for calculating the depth of footing, we know we have to check three criterion and have to take the highest value of small d depth. The three criterion are one-way shear criterion, two-way shear criterion or punching shear criterion, and bending moment shear criterion. So first, by one-way shear criterion, the critical section is at D from the face of column. So first check out the diagram of footing. So this is the diagram. Shorter side is 1.80 and longer is 3.60. Okay. So critical section is at D from the face of column, as you see here. Critical section is at D from the face of column. Now shear force in longer direction is 266.21 into 3.6 into within bracket 1.8 minus 0.3 by 2 minus D. So here 266.21 is PU multiplied by 3.6, that is side, longer side of the footing, within bracket 1.8, that is longer side of sorry, that is shorter side of footing minus 0.3, that is column, by 2 minus D, that is equals to 958.356 into 0.75 minus 958.356 D, that is equals to 718.767 minus 958.356 D. Now shear force in shorter direction is Pu into x in bracket a minus y minus b by 2 minus d. So that is equals to 266.21 into 1.8 within bracket 3.6 minus 0.6 by 2 minus d, that is equals to 718.767 minus 479.178 d. So this is equation 1. Now shear force resisted by concrete is tau cxt. We can assume here the percentage of steel reinforcement is 0.2. So for 0.2% of steel and M20 grade of concrete, tau c is equal to 0.32. So shear force resisted by concrete is equals to 0.32 by 10 cube into 10 to the power 6 into 1.80 into d, that is equals to 576 d. Now we have to equate equation 1 and equation 2. Before that, just see the picture again. In left side you can see the one-way shear is along longer direction, and in the picture in right side the single shear is light in as along shorter span. Now equating equation 1 and 2, we will get the value of depth d. So some 718.767 minus 479.1780 is equals to 576d. That is equals to d is equals to 0.681 meter. So as per by value the one way shear criteria, as per one way shear criterion, the value of d is the value of d is 0.681 meter. Now next step is depth of footing by two-way shear criterion. The critical section is at d by 2 distance from the face of column. So you can see here the picture for two-way shear or punching shear. So every side is shear is shown. So you can see the critical section is at d by 2 distance from every side. Now the shear force at critical section due to shaded area is 266.21, that is pu, into 3.6 minus 1.80 minus 0.3 plus d bracket close into within bracket 0.6 plus d bracket close, that is equals to 1725 minus 266.21 within bracket 0.18 plus 0.9 d plus d square, that is equals to 1677.08 minus 239.59 d minus 266.21 d. So this is equation 3. Now punching shear resisted by the section is tau c into area A. So tau c is 0.25 root over fck, that is equals to 0.25 root over 20, that is equals to 1.118 Newton per millimeter square. So capital A, area of critical section, is equals to perimeter into d, that is equals to 0.30 plus d plus 0.60 plus d bracket closed multiplied by d. So that is equals to 0.9 plus 2d into d, that is equals to 0.9d plus 2d square. So shear force resisted is 1.118, that is tau c into 10 to the power 6 by 10 cube into within bracket 0.9d plus 2d square, that is equals to 1006.2d plus 2236 d square. Now we have to equate equation 3 and equation 4 to find out the value of d. So by equating this equation we get 1677.08 minus 239.59 d minus 266.21 d square plus 1006, that is equals to 1006.2 d plus 2236 d square, or d square is equals to 0.498 d minus 0.67, that is equals to 0. So from this equation we have to apply Sridhar's formula and we can find out small d, that is equals to minus 0.498 plus minus root over 0.498 plus 4 into 0.67 by 2. So d is 0.607 meter. Depth of footing by bending moment criterion. This is the next step. So as by two-way shear, we check that the value of d is 0.607 meter, that means 607 mm. Okay, So the next step is depth of footing by bending moments criterion. Okay, for bending moment criterion, first of all, see this figure. These figures. In left side, the zone of bending moment shown shown along shorter direction, and in figure of which is in the right side, the bending moment zone is marked for along uh, longer direction. So we have to calculate this value. So for shorter direction, the length along y-axis is definitely 3.6 minus 0.60 by 2, that is equals to 1.50 meter. And for right side figure, bending moment along y-axis, the length along x-axis, the shorter direction is x, that means 1.80 minus 0.3 by 2, that is equals to 0.75 meter. Okay, so now bending moment in longer direction will be 266.21 into 1.80 into 1.5 into 1.5 by 2. So just beside this, I have written the formula. So this is as per formula. So that is equals to 539.08 kilonewton meter. Now bending moment in shorter direction, written the formula again. This is equals to 266.21 into 3.6 into 0.75 into 0.75 by 2, that is equals to 269.54 kilonewton meter. Hence bending moment in longer direction is more, so we have to take this for consideration. Now moment of resistance in longer direction, mu is equals to 0.138 FCK into d square, that is equals to 0.138 20 into 1800 d square, that is equals to 4968 d square Newton mm. Now we have to equate equation 5 and 6 to calculate the value of d. So that is equals to 539.08 into 10 cube into 10 cube, that is equals to 4968 d square. So d square is equals to 539.08 into 10 to the power 6 by 4968, that is equals to 108510.5. So d is equals to 330 mm or 0.330 meter. Now out of equation A, B and C, the value of equation A, that is 681 mm, is highest. So depth in consideration will be 681 mm. Now using 16 mm dia bar and 50 mm clear cover, we have to calculate overall depth. Capital G is equals to 690 plus 8 plus 50 and the half dia plus clear cover, so that is equals to 748 mm, 750 mm. If the overall depth is 750 mm, then the effective depth small d is equals to 750 minus half dia 8 minus clear cover 50, that is equals to 692 mm. Now area of reinforcement. Now area of reinforcement, we have to calculate. This formula is given in Annex G of IS 456 2000. mu is equals to 0.87 Fy AST to D within bracket 1 minus AST Fy by BD FCK. For longer direction, 539.08 into 10 to the power 6 is equals to 0.87 into 415 into AST into 692 into within bracket 1 minus AST into 415 by 1800 into 692 into 20. So this is equals to 249,846.6 AST within bracket 1 minus AST by 60028.92. That is equals to 249,846.6 AST minus 4.168 AST square, or AST minus 6000.41 AST plus 129.5 into 10 to the power 6 is equals to 0. So again we have to apply Sridharacharya's formula. So AST is equals to 60030.41 plus minus root over 60030.41 square minus 4 into 129.52 into 10 to the power 6 by 2. That is equals to 2225 mm square. Now using 16 mm diabar, the spacing will be 201 by 225 into 1800, that is equals to 162.60 mm. So you can provide 16 mm diabar at the rate of 160 mm center to center. Now for shorter direction, 269.54 into 10 to the power 6, that is equals to 249,846.6 AST within bracket 1 minus AST by 60028.92 bracket close is equals to 249,846.6 AST minus 4.162 AST square, or AST square equals AST square minus 60030.41 AST plus 64.76 into 10 to the power 6 bracket close equals to 0. So again apply Sridharacharya's formula, and AST equals to 60030.41 plus minus root over 60030.41 square minus 4 into 64.76 into 10 to the power 6 by 2. So AST is equals to 1098.91 mm square. Now minimum reinforcement at rate of 0.12%, that means 0.12% of area, that is equals to 0.12 by 100 into 3600 into 750 is equals to 3240 mm square, which is greater than 1098 mm square. So as per IS code provision clause number 34.3.1 page 65, reinforcement in central band by total reinforcement in shorter direction is equals to 2 by beta plus 1, where beta is equals to y by x, that is equals to 3.6 by 1.8 equals to 2. Hence reinforcement in central band by 3240 is equals to 2 by 2 plus 1, or reinforcement in central band is equals to 2 by 3 into 3240 is equals to 2260 mm square. So this reinforcement shall be distributed in central 1.8 meter bandwidth, as half of 3.6 meter in 1.8 is 1.8. So reinforcement, spacing of 16 dia bars is equals to 201 by 2260 into 1800 is equals to 167.5 mm, say 160 mm. Now provide 16 mm dia bar at the rate of 160 mm center to center in central band. So we have to design differently for central band reinforcement. So balance area of steel to be distributed in outer bands is 3240 minus 2260, that is equals to 1080 mm. So spacing of 16 mm diabar is equals to 201 by 1080 into 1800 is equals to 335. So maximum spacing allowed is 300 mm or D, 692, whichever is less. So we have to provide 60 mm dia bar at the rate of 300 mm center to center for outer bands. Now the last step, we have to check for development length. So so development length we have to check from clause number 26.2.1.1 of IS 456 2000. LD is equals to 0.87 fy into dia by 4 tau bd is equals to 0.87 into 415 into 16 by 4 into 1.92, that is equals to 752.2 mm. Now available length in shorter direction beyond column face is 1800 minus 300 by 2, that is equals to 750 mm, which is less than 752.2 mm. So hence okay. Now provide 90-degree bend at free end of the reinforcement as per IS code provision. Anchorage value of 90-degree bend is 8 dia, that is equals to 128 mm. Okay, so that way we have to provide bend of bar for anchorage. So total anchorage length is equals to 750 plus 128, that is equals to 878 mm, which is greater than 752.2 mm, hence okay. Now see the reinforcement detail. Okay. Here is outer band and here is central band. As for calculation, we have drawn and write this. This is the plan and this is the elevation. So that's all for this lecture. Thank you for listening.